Please join me in welcoming to the Distinctive Voices podium, Dr. Nicole Lighthoff.
Okay, first of all, thank you so much for being here today. I'm a little bit of an unconventional speaker. If you've been here before, I might walk around a lot, so hopefully the camera guys can follow me. I'm so honored to be here giving the Seymour Benzer lecture. A related note on some of his contributions, it was mentioned that I did a PhD in gerontology, and it turns out we learned an awful lot about fruit flies. Fruit flies are an amazing model organism to look at longevity, and there's been a lot of research done on them. So my own training benefited from some of the contributions that Dr. Benzer made to science, so I thank him for that. I also want to say that I'm talking about aging today, and it's going to be a positive story. Yay! I like getting applause at the beginning before I even deserved it. So I know we have many retired folks in the audience. That's my crowd. These are my people. These are my participants. And so I thank you all for allowing me to sort of communicate the science that I've been dedicating my life to back to the people that it matters most to, right? This is my target audience. And those of you who are younger, we're all aging, and it's a group that we all will transition into at some point. So it's very relevant to all of us on a personal level, but also as we think about caring for our loved ones and planning for our future. So with that, I'm going to begin. How do we think about the aging brain? When we use this kind of phrase, what are the images that come to mind? So I recently gave a talk on this topic in Orlando, where I live, aging capital of the United States, retirement community to the stars. And this is the picture that they put on my talk advertisement. They didn't get the memo about the positive story. I don't know if you can tell, that's like an icy lake. It's very abysmal. So when we have this term come to mind, sometimes we fear the worst. We think about Alzheimer's disease. Raise your hands. When I said aging brain, did we think about dementia? Okay. So that's common. The good news is we have awareness now about dementia, and that's a positive thing because it generates research dollars, and it is truly devastating to the people that it affects, not just the patients, but their loved ones. But it's not the only story. So when we look at the lifespan, yes, it's true that aging is associated with some increasing losses. So we're losing out on the gains, we're increasing the losses. But the norm of cognitive aging does not end in dementia. We have cognitive aging without dementia, and a recent study looking at waves of data collected in 2000 and 2012 from a very large scale study, the Health and Retirement Study, found that when we look at these age trajectories, overall people above 75 years old, the rates when they looked at the data in 2000 was only 11.6% of people over 65, and it's dropped. That's already some good news. So I'm working for my applause. Now, I didn't do any of this research, but this is good. They are saying that some of the picture here is related to better treatment of cardiac conditions and diabetes, and it's dramatically decreasing the load on the brain over different cohorts and generations as we improve our medical services and treatments. That's already positive. What about the possibilities? That's just that norm. Jeanne Clement, who is French, was the oldest documented life. She had 22 years of longevity, and she died without dementia. This is her life. It was told that she knew Vincent van Gogh, or she at least met him, although I think everybody who knew the truth of that story was dead. So she could say whatever she wanted. She died in 1997. At age 85, she took up fencing. She rode a bicycle until she was 100 years old. And I didn't put it on here, but she quit smoking at 117 because it was bad for her health. She said, I see badly, I hear badly, I feel bad, but everything's fine. What did she leave out that wasn't so bad? Her mind. Well, it's her sense of humor. Yeah, you're right about that. Here's another joke. I've got only one wrinkle and I'm sitting on it. That translates from French to English very well. So she understood that optimal aging, a lot of it is about keeping the mind sharp. And somebody who lives as long as her without dementia has the ability to give us hope that we too can live such a great life with a sound mind. I used to work at Stanford. I started working there when I was 21 years old. I was really interested in a lot of these topics about aging and longevity. And so I got a job in the psychiatry department, and I was working on a study looking at risk factors for dementia. At that time, I thought I wanted to study dementia and help to find a cure. And something that I realized when I was there, because I would interview these participants, I would do cognitive tests and all these psychosocial measures, and I'd take biosamples, and I'd watch them do their cog testing, and we do things like this. Remember all these words, 15, drum, curtain, bell, coffee, school, parent, blah, blah, blah. I used to recite these in my mind. I read them so many times. And so the participants would hear me go through the words, and then they'd repeat them from memory. And I had participants who would recall the list, all 15, in order on the first try. You'll notice there are 5 columns here. That's because that's how long it usually takes to get to your peak performance. And I am sitting there at 21 years old, working with participants who are between 65 to 102 years old, and many of them outperformed me. My memory is terrible. So how did they do this? I was totally baffled. They clearly have something going on that I don't have, despite the fact that they're supposed to have this increasing level of loss. So I wanted to change my track. I wanted to study super seniors, optimal agers. I became really inspired to understand the highest level of where we can be when we age. And so I went to USC, to the Andrus Gerontology Center, or the Leonard Davis School of Gerontology, to study this very topic, optimal aging and healthy brain function at USC. One of the people that I learned about when I was there is Paul Baltes. Paul Baltes was a German psychologist and would be called the father of modern psychology of aging. And he came up with one of the first of these positive views about aging, not all about pathology and disease and decline, but optimal aging. How can we shoot for that, and how can we understand it? What are its characteristics? So he came up with this theory in 1980, and it involved 3 components. The first is selection. We should select achievable goals. Second is optimization. Continue to develop your strengths. Compensation. Change goals in response to losses. And another feature of that, you can use different strategies to achieve the same goal. So how might this look? You can play the songs you know rather than learning new songs. You can continue to enhance your ability to play the songs that you know with even more flair and panache. You can change your goals in response to losses. If you have arthritis, you can choose songs that have a smaller range of movement, perhaps. Or if you sustain an injury, you can kind of favor one hand over the other. If you're having problems with your breathing, you can, pick songs or play in places where it's a sort of small crowd rather than a very large one, or open air where you need more breath. And then using different strategies. Playing with a band, for example. It's not all on you. You're not the solo artist. You can play as part of an ensemble. And so all of these are ways to feel successful, to have legitimate success as you're getting older in the face of losses. So Balte's message is essentially that to age well, we have to have an adaptive capacity, and we can adapt in many different ways. And you'll notice that I haven't talked about cognition here, because this theory wasn't really applied to, strictly speaking, cognitive functions, meaning the functions of the mind, not including things like emotion. Nor was it really applied to things like how the brain ages. So that's what I'm interested in, taking Balte's torch and moving that forward with this, cognitive aging kind of question. So what I want to know is, what are the key or keys to optimal cognitive aging? Can we learn some of these lessons? Can we test some of these theories in that domain? So the first thing we have to have, if we want to move this theory forward into the cognitive, mental, and brain realm, is some different kinds of tools. Because we can't observe everything that we want to know about just by asking people. So we develop behavioral experiments to do this. A lot of our experiments are computer-based. In this task, people are given different characters. These happen to be Japanese characters, but our participants don't know what they are because they're not fluent in Japanese, nor can they read it. And over time, they learn that if they select one or the other of them, they're more likely to get positive feedback. This is like if you got a neighbor that just moved in and you're trying to figure out if you like them or not. It takes a few experiences, right? And not everybody's having their best day every day. So sometimes they give us negative experiences, but on the whole, what you're trying to learn is, what are the things, who are the people that give me the most positive feedback, and you choose to spend your time with those people. So it's sort of like that. So we can develop experiments that let us understand learning as it happens. We can also look at neurochemical biomarkers. So we can safely assess different markers for things like stress. Yes, I make my participants spit in a tube. That's who I am. Because we want to know something about stress. And so if we take saliva, we can actually assay that and look at measures of cortisol. Many folks in here know about cortisol. That's one of our primary stress hormones. And we can understand how the body and the brain is responding to threats and challenges and stressors. And so we can measure those changes over time. Another one of the tools that I often use is functional MRI. So fMRI, we have these beautiful magnets, very high-powered magnets, but the nice thing about fMRI is that it just takes advantage of magnetic properties of blood. We don't have to put anything in the body, and it's a pretty safe procedure as long as you don't have anything like a pacemaker. So there are some people who are excluded, but by and large, healthy folks can do this without much of a problem. They lie on this little table, they wear this little, they call it a coil. Some of them look more like a Darth Vader mask, but nonetheless, they go into this tube and they can do little experiments. People lie on their back and they've got a mirror above their eyes, which is nice. It helps relieve claustrophobia. And they will see through the mirror a projected image that's sitting outside of the screen. That's where we can project our computer-based tasks and let people play games in there. And we can monitor their brain activity while they're lying there in the scanner playing these games. And they've got a little button box or some kind of other thing so they can tell us what they're thinking about or respond or learn. And we can reliably match up different brain areas with the levels of activity, matching those up with what's going on in the task at the time or how much people are learning. And so we pay attention to the peaks and valleys of this activity that's in the brain as mapped by this MRI procedure. So by a show of hands, how many people have had an MRI in the audience? A lot. You could all be my participants, and if you come to Orlando, you should please look me up, and I will enroll you in a study. So if you've had one for your back or your knee or something like that, the main difference is just that instead of looking at a static 3D image, they basically take a 3D picture of your body part. We take a bunch of those 3D images back to back to back every couple of seconds, and we use that to monitor brain activity in specific regions as people are doing these kinds of tasks. So fMRI, the first studies, the original study was like 1990, okay? But we didn't really get going with it until the 2000s or so. This is the increase in number of publications with functional MRI in the title or abstract over time. The first studies of healthy cognitive aging started around 2000. So there was like a 20-year gap in there where we weren't able to inquire much about the active mind without doing things like subjective ratings and behavioral markers on these kinds of cognitive experiments. So I can use all of these tools to ask some critical questions about what this kind of optimal aging looks like. And what I'm going to talk to you about today are sort of three themes of the findings that we've been able to get using these tools. And this is the outline for my talk. So what I've been able to find about the characteristics of optimally aging brains. First of all, they are responsive to external pressures. One of them I'm going to be talking about is stress, okay? You might think that stress is just negative. It's not. We have it for a reason. It's an important signal from the outside world. There's maybe something we need to pay attention to. And so it's very adaptive to have a strong response to stress that plays out in your body system and affects your cognition. One of the second lessons is we have little to no functional decline in specific brain regions among our optimal agers. I'm going to say that again. Their brain signals, in some cases, are indistinguishable from people in their 20s. We're talking about people, average age in my participant pool for the older adults is 72 years old. It's incredible. The third thing is, we also, as we age, have the ability to compensate for functions that are vulnerable. Even my super agers have some level of decline. However, the best among them have the ability to recruit extra help on those functions where they struggle. And now we're going to talk about it. So, starting with neurofunctional responses to external pressures. How many have heard about dopamine? Nice. Good. So you're a highly educated group of people, but for those of you who are unfamiliar, dopamine is a neurotransmitter, okay? And so neurons, these are two neurons here, they talk to each other through neurochemical signals. Dopamine is one of those kinds of neurochemicals. So at the synapse where these two neurons are almost touching, we can have the release of dopamine into this in-between area, and that helps with the transmission of information from our top synapse here to the next one down the road, so from neuron A to neuron B. So dopamine is all over the brain, but there are some areas of the brain that have more neurons with a lot of dopamine receptors than others. So I'm going to come back to this picture of the brain again. This is just a cartoon to give you an idea, but there are several areas that I've done a lot of research on, and we're going to come back to this several times. One of them is the nucleus accumbens. It's nested deep in the brain. This is the cortex, the wrinkly part. That's what we normally think about as the brain, but there's stuff underneath that, okay? And in terms of evolution, the stuff underneath is what we think of as very evolutionarily old. It's very similar in all mammals and some reptiles, birds. Animals have these basic structures underneath, and they function relatively similarly. So nucleus accumbens is one of them. Prefrontal cortex. This is a region that makes us special. We have more of this region here, which is right behind the bridge of the nose, behind that orbital area, than other mammals, than all other animals, in fact. And the hippocampus. How many have heard about the hippocampus? Yes, you have. Why? Because of Alzheimer's disease. Good, they're getting the word out. So I want to tell you more about its function outside of the dark and gloomy discussion about dementia. So dopamine receptors are found in all of these 3 regions. It's also found elsewhere in the brain, but a lot of high concentration in these regions. So it turns out that when we are stressed, that increases phasic levels of dopamine. How do we know this? So this is an experiment done with model species. These are rats. And when these animals are stressed, this is stress exposure here, starting at time 0. This is cortisol on the bottom, that's stress hormone. We see that dopamine levels peak right here, and then they taper off and peak again when the animals are released from this stressor. So we see dopamine levels increasing in these black dots in the prefrontal cortex, in the nucleus accumbens, which I talked about first on that other brain, and then with the little stars here is in the hippocampus. So while you might think that stress just enhances stress hormones, it doesn't. It has other effects on the body, on the brain. So one of them is it enhances levels of dopamine in several regions. So I'm going to not talk about why stress is adaptive for the dopamine system, but you can ask me about that after the talk. I'd be happy to talk with you about it. But just know that it does, and it does have an adaptive function. So we see these nice peaks here, and they correspond with peaks in stress hormones like cortisol, which is mapped on the bottom. All right, we have a problem in aging. We see that our baseline levels of dopamine decline, dopamine neuron activity. So here is a younger brain as imaged by PET, so positron emission tomography. It's different than fMRI. It's more dangerous. You have to inject a radioactive isotope into the bloodstream. And then we have older adults here. Now, I haven't told you what this bar means. Do you think that purple is good or bad? It's not great. Okay, cool colors mean that you have a loss of dopaminergic activity at rest. These people are just lying in the PET scanner, resting. Well, what we didn't know is about adaptation to challenge. So what I wanted to know is, can healthy older brains adaptively respond when exposed to stress? So remember I said that stress enhances dopamine. These people are just lying in the scanner at rest, and their dopamine activity is quite low. But if I challenge you by forcing you to be exposed to a stressor, can your brain adapt and mount that response? And so we can look at that in a couple different ways. So one of the easier ways to do this is we have tasks, cognitive tasks that we know require dopamine. They are called dopamine-dependent tasks. And so we can have people play these games and see how they perform. So one of those is that task I was telling you about earlier, but I wanted to make it a little bit more understandable. So when you think about learning from feedback, remember finding the neighbor that you like, right, over time. This is like a positive feedback or reward feedback. I'm exposed to you, I choose to hang out with you. Are you giving me happy, smiley faces and compliments, or are you being mean and rude? So that is this kind of reward learning. It's here classically when we have an action and we immediately get feedback. I tell a joke, you laugh. Let's try it. I told a joke. Oh, my dopamine, it's going through the roof. Okay. You can also have this kind of aversion or avoidant type learning where you get the negative feedback. I'm hoping for none of that today. So optimally, when we are rewarded, we will go toward those things that are rewarding, and that requires dopamine. How do we know that? Well, definitely one of the ways we know is we look at patient groups who have problems with the dopamine function. Parkinson's disease is a classic case. If we study healthy seniors versus Parkinson's patients who are off their dopamine medication or on their dopamine medication, we can see what happens to their task performance, and we can say with pretty high certainty whether dopamine is important for the task or not. So here in the positive feedback condition, when patients with Parkinson's are off their meds, their ability to learn from positive feedback drops. But when they are on their medications, they're actually better than the controls, significantly better. They do quite well at this. And so this is one of the ways that we can be pretty sure dopamine is involved in this learning from reward, learning from positive feedback. Very important. So this is that task again I showed you. We just have people learning these kinds of symbols. Some of them more frequently lead to positive feedback. They get a correct response, or they get paid $1, or they get a happy face. It kind of doesn't matter actually what the outcome is, so long as it has a positive valence. Whereas other cues, when they're selected, more frequently lead to negative feedback. So people want to avoid those. Remember that stress affects dopamine levels, and dopamine helps us do this kind of task, learning the association between this symbol and that correct feedback. So, how do we look at adaptive responses in older people? I made them spit into tubes to measure their stress hormones, and I also exposed them to icy cold water. So that's the stressor. We had people hold their hand in ice water for 3 minutes or warm water. So if you were lucky to be the control participant, you just put your hand in body temperature water. Otherwise, you put your hand in the ice water. We then did those saliva biomarker samples to see if people actually had that reliable increase in their stress hormone. I can't measure dopamine. I would love to do that, but we can't actually measure it. I can't even just do it through blood actively. So what we do is we look at stress hormones as a proxy, because we know that they vary at the same rate. Stress hormones are nice because I just have people spit in a tube, and that's easy. And so we showed that by having people exposed to this cold water stress, in the black bar line here, they're reliably higher in the stress hormone than the control group. And we also took subjective ratings to be sure it was painful and they didn't like it. And both of those showed that the stressor was effective. And then after that, we had them do the learning task. Now recall that what we expect to happen is that when people are exposed to stress, it bumps up those dopamine levels. And that should help them, like the Parkinson's patients on their meds, to do better at learning from positive feedback. If the aging brain is optimally adapting to that external stimuli, they're going to do better. What happened? We had equivalent benefits of stress in younger and older adults. I didn't even expect this. I was hoping they would show some benefit, but I wasn't expecting them to be equal. In the younger adults, we see on accuracy for positive feedback learning, they go up. They increase under stress. That's what we expected. But they're healthy younger adults with lots of high-functioning dopamine neurons. One of my mentors and a wonderful collaborator, Mara Mather, who's still at USC, we developed this theory called STARS, which is that stress triggers additional reward salience. That's the theory behind this, that when we're exposed to stress, we are sensitive to stimuli in our environment that give us a rewarding feeling, like food or a kind person or something like that. But how about the older adults? The older adults also show this benefit. Their performance increased when they were under stress. So it's so contrary to what we might think. You think, oh, I'm stressed out, I'm not going to be able to do this task. Guess what? I want to show you this. Look at this black bar in the older group. If we knock these out, they are equivalent to the younger adults in the control condition. That means by stressing them, we got them to perform at the level of 20-year-olds at USC. So they got the same benefit as healthy seniors did as the younger adults, which was shocking. So although you can see their performance is lower on average, we couldn't get rid of that. But under stress, we were able to bring them up to the level of younger adults, which was so exciting. So the evidence from this first study is that we have this adaptive capacity when we're in that healthy aging group. And we can respond appropriately to external stressors. We have the ability, despite the fact that maybe our dopamine neurons at rest are not quite as active, when there's an appropriate trigger, a stimulus from the environment that we need to respond to, our brains can do it. Now again, these are you folks, okay? If you are bedridden, at home, you're very sick, different story. But everyone in this room is likely to be in my optimal aging group by virtue of you coming here and participating in this kind of event. So again, even though the story might be grim, overall, we have these optimal agers that actually can perform. This is our older group on the right, our younger group on the left, and we get that boost up to equivalent level of performance in young when we expose them to stress. So next time you feel stressed, just think, what are all the wonderful, rewarding things I can learn about? And maybe that'll help you to apply it to your life. All right, number 2, preserve function in select brain regions. Now, I said, even in the most ideal case, we do have some decline, both in structure and in function, but there are certain brain regions that are quite resilient to decline in aging. And we're going to focus on 2 regions here that I wanted to test which of them is more resilient to the aging process. Again, the nucleus accumbens tucked in here, and the hippocampus. So we go back to our same learning task. I'm really interested in how people learn about the value of things. Because ultimately, all of us, when we're trying to achieve our goals, we have to find actions that get us to the best possible outcome. And so what we can do is change this task just a little bit so that it favors one brain region or the other. It turns out that if you have immediate feedback, the task really needs this nucleus accumbens. If you delay the feedback, that smile, that compliment, that angry insult, just a little bit, a few seconds, the task then requires more help from the hippocampus. Interesting, right? So we know that this kind of learning from feedback, it involves different memory regions if we just tweak the task just a little bit. How do we know this? Again, we can look at patients who have problems in certain brain regions very reliably. We go back to Parkinson's patients. When feedback is immediate, look what happens to their performance. They're at chance, 50%. We know that they have dysfunction in their nucleus accumbens. That's a part of that same set of regions in the basal ganglia. When you delay feedback for 7 seconds, they perform at the level of controls. I'm going to tell you a lot of surprising things. I'm going to tell you that stress can improve your learning. I'm going to tell you that if you make Parkinson's patients wait for 7 seconds to get a reward, they will do as well as controls. That waiting helps them by relying on a different brain region that they still have well intact. How about we look at a different group of patients? Amnesics. Amnesics have lesions to the hippocampus, but they have a very nicely intact nucleus accumbens. When feedback is immediate, they do as well as controls, but look what happens when we delay the feedback for 7 seconds. They're hitting the floor here. So for them, waiting seems to rely on the region that they are having problems in, the hippocampus. Again, these patients have lesions there, likely because they had some intractable epilepsy where it had to be removed, or they might have had some kind of a stroke or something like that. And so that's the problem there. If they get the feedback right away, they do just fine. So again, if we have problems in the nucleus accumbens, we have an impairment selectively for learning from immediate feedback. If we have problems in the hippocampus, we have a selective impairment for delayed feedback. All right, so just to be doubly sure that this is what's really going on, others have done this research with younger adults using functional MRI. They peek inside the brain, they don't have to damage anything to get this information, and they find that when feedback is delayed, you see more activity in the hippocampus for that same kind of task, and in these young adults, when feedback is immediate, you see more activity in the nucleus accumbens using functional MRI with nice, healthy people. So it seems like these brain regions are definitely involved, and they've got really specific jobs to do. So which of them ages more rapidly? And how much do they age relative to younger adults? So do we see some similarities or dramatic differences in both? Well, when we look at brain structure to make some hypotheses about these, we can do things like measure how much volume a region has. That's somewhat indicative of how many neurons are there, what has died and what has lived. And you see that there are different patterns In the nucleus accumbens, there's a steady decline, and you can tell your kids or your grandkids that the decline in these regions functionally, structurally begins in the 20s, right? I'm already there, well past. Whereas the hippocampus has a different trajectory. It tends to peak in volume later in life, 40s and 50s, and then it declines. So this is cross-sectional data, meaning we're measuring people at just one point in their life, not over time. And this is what the cross-section looks like if we look at brains of these different ages. So it looks like for my seniors, because again, my participants generally are 60, 65 and up, it looks like there's more rapid decline in the hippocampus, but this is just the structure. This is really about the number of neurons and how plump those regions are. It doesn't say anything about function, really. To do that, we have to actually make them do tasks and look at brain activity. So what I wanted to know is, do healthy older brains have different patterns of functional change by structure? So now we have to look at the function and see, I don't care how many neurons you have in your hippocampus, how well do they work? So we use the same kind of feedback task, but we have that one tiny tweak, remember? Where sometimes people get feedback right away, and sometimes they have to wait. Now you'll notice that the feedback in this case are pictures. We did that because we also wanted to query people's memory about the specific feedback that they got. So people in my study here, they were trained to associate indoor scenes with, say, a good outcome and outdoor scenes with a bad outcome. And so we trained them on that first, and then we had them do the task. Because we think that if the hippocampus is involved, they're going to have better memory for those pictures. So that was another kind of question that we had, a little side question. But the main manipulation is really simple. And actually, we asked people, hey, do you remember the cues that you had to wait 7 seconds for the outcome? Their performance was terrible. Basically, everybody guessed about the delay somewhere right in the middle. So the delays were either 1 second or 7. People's averages for both was about 3.5. Okay? So they really didn't know very well which was which. In terms of behavior, the purple lines represent the delayed condition, and the green bars, the immediate feedback condition. Dashed lines are older adults. You can see that overall the older adults are a little lower on performance, but it's very consistent. What that means is they started out a little worse, but they got better over time at the same rate as younger adults. This is a good thing because this indicates that their learning was equivalent. They started out a little worse from the beginning, but if they were given enough trials, they would get to that same asymptotic level. So the learning was equivalent. Again, these are my super seniors. They're doing a hard task in a scanner environment, which is a little stressful, and they're doing basically at a performance level as well as younger adults. And by the way, this paper is currently under review, so you guys are getting the super sneak preview of this data. You will be among the first to know, so good on ya. We looked at their brain activity because they did this task in the scanner again, and across the feedback timing conditions, you see here's the nucleus accumbens, here's the hippocampus. If I covered the top of that, could you tell me which is younger and older? I don't think so. They look the same. But remember, we think the hippocampus is involved in the delayed learning, and the immediate feedback learning, we need the nucleus accumbens. So here I'm looking across both, and they look basically the same. But if I divide them up, we see something very different. In younger adults, as we expected, in the nucleus accumbens, when feedback is immediate, the green bars, a lot of activity in the nucleus accumbens. When the feedback is delayed, that goes way down and the hippocampus takes over. That's exactly what we expected. That's consistent with what people showed in the patients and other fMRI studies. But what happened in my older adults? Here's the nucleus accumbens activity. You can see this bar for immediate feedback, it's indistinguishable from younger adults. You're at the same level, okay? Again, the structure might have declined, but this is function. And they're just at the same level. You can see that the nucleus accumbens actually, in the older adults, when the feedback is delayed, they also recruit some of that. So they're using the nucleus accumbens for things that younger adults do not. What about when feedback is delayed? You'll notice overall less activity in general in the hippocampus. But the biggest thing is the older adults do not show this big bump when feedback is delayed. This indicates the hippocampus is not doing what it's supposed to do when feedback is delayed. So even though the older adults have great behavioral performance, similar to young in terms of their learning rates, even though the striatum, so this nucleus accumbens region within the striatum, it's looking really similar in my super agers, the hippocampus is still showing some decline. So there are some limits to this stuff. But that means that when we know where our vulnerabilities are, we can take advantage of that. We can focus on our strengths. Remember, we play the songs we know. We select the kinds of tasks that are best for us. This means that the best kind of learning that we can do as we get older is feedback right away. Don't you make me wait. I'm telling you, I want to know how you're feeling within 7 seconds and no less. 1 to 2 is better. So if you're going to give me applause at the end of this, be sure to do it right away. I cannot wait. So that's sort of the message here. So again, the evidence for this adaptive aging brain is that we see very minimal functional decline in select memory regions. Here we focus on the nucleus accumbens within the basal ganglia, this, remember, very evolutionary old structure, nicely intact in our super seniors. So even though we see decline in structure, we see similar differences in strengths in the function. All right, number 3. Compensation. All right, now things have gone badly. We've got some tasks that we're struggling with as we get older. What do we do then? Is there any hope for us? Yes, there's hope. I wouldn't be here if there was no hope. So I have been very interested for a long time in decision making. One of the reasons why I really liked studying decision making is because it's very complicated. It involves basically every other kind of cognitive function. Memory, learning, we also have emotion in there. We have to process rewards and punishments. We have to rely on our world knowledge sometimes as well. So one of the things that makes decisions difficult oftentimes is increasing the memory load. How many features do I have to remember or integrate? How much information do I have to process in order to make a choice? And Amazon is a perfect model organism for this kind of question. I was recently shopping for a cell phone. This is my search history list. Page after page after page of comparisons. And you look at them sequentially. I've done page 1, and then 2, and then 3, and it's increasing the memory load. So now I have to remember, what was the last one I saw? What was the one before that? And I'm telling you, I'm aging like everybody else, but I'm not yet in my older participant group, and these kinds of things not only stress me out, but make me feel overwhelmed. The other thing is, even within a page of information on these shopping websites, there's a lot of info. So you have memory load just from kind of scanning from feature to feature within the page. So the information load is very substantial, so we often use these kind of shortcuts or heuristics. I'm going to go with what the average consumer rated for this product, and that'll tell me generally how good it is. So we built an experiment around this idea. So this is my consumer choice task that I developed with my colleagues at Duke. And we had different products that we stole from Amazon, and we just assigned them little simple ratings. More stars is better, and few stars means it wasn't a very good product, and you wouldn't want to pick that. And then we just put people under different levels of memory load. So sometimes we wouldn't have to do much at all. We've got both the competing products. I want to choose the best lawn chair. Which one do I pick? The one with the higher star rating. I can just look at them and tell you that. That's a perceptual decision. It requires no memory whatsoever. We can also have situations where green means go, keep shopping. Red means stop, make a choice. This one means I just looked at a watch. Now I have to make a choice between the one I've got on the screen and the one I just saw. Yes, that involves memory. Very simple though, working memory. Even if I wasn't paying much attention at all, I could probably remember what just happened. Here's the hard ones. Sometimes there were 3 intervening trials in between. I've been shopping, making choices, other choices, and then I come back to this dreaded lunch bag. And I have to remember how many stars the first one had so that I can say, do I want to pick the one in front of me now, or am I going to go with the one that I saw earlier? Again, this is the most simplistic form of this decision, but guess what? It's quite challenging. And so we're able to look at this brain activity associated with these different conditions of increasing memory load involved in choice. And I've told you already, my participants are awesome, and their accuracy was equivalent to younger adults. I'm no longer surprised by them. They astound me every day. And so whether there was no delay, an immediate delay, or that 3-trial lag, we had equivalent performance in younger and older adults on accuracy. Older adults were a little slower to make the choices. That's pretty normal, but the accuracy is the main thing that we cared about. So I want to point out something here. I've shown you 2 experiments where we didn't see very many behavioral differences between younger and older. What's going on is that the brain is changing the way that it does that same problem. And that's what we want to know. How is it doing that? How does it reorganize itself? How does it take advantage of its own strengths? And it's not like you could just say, hey man, let's get some more hippocampus going on over here. I mean, you can try. But a lot of this would be considered like an organic kind of organizational shift. That's why when I was introduced, I was saying, my goal is to find a model of how decision-making works over the lifespan. Because a deciding brain that's 20 may look quite different from a deciding brain that is 70, but behavior can look the same. These are not equivalent things. It's reorganizing and taking advantage of its strengths. So we have these really high levels of accuracy in our older adults on this memory-dependent decision task. Do we have evidence of neural compensation? Now, neural compensation is a very specific term, so I want to give you a sense of what that actually means. For that, I will rely on former Governor Arnold Schwarzenegger, and by the way, I am proud to say one of my college diplomas has his signature on it. So I already have an autograph, and I didn't even have to pay. Well, yeah, I sort of had to pay, but anyway. Back when he was Mr. Olympia, he was quite strong, and he could curl these 100-pound dumbbells in just one hand. These days, he's probably using 2 hands to do the job, and we don't know what this weight is. It might even be a little less, but he's getting the job done. Now, I had to check his Twitter because I wanted to make sure he wasn't still very ailing because, he had a health event recently. He's okay. Don't worry. He continues to move along, and he's probably back in the gym already. So Arnold is compensating. He has the same goal to lift heavy weights, but he may use 2 hands where he used to use 1. That's one method of compensating. So what we want to know is when people are making decisions, how might their brains compensate in the same way that Arnold is compensating? Can we use different brain regions to help support the functions that used to be done by maybe a smaller group of regions, or regions that are maybe declining more in aging? So for that, remember, we had our consumer choice task. We saw this equivalent level of accuracy, and what did we find? We found that this region right behind the bridge of the nose, ventral medial prefrontal cortex, ventral because it's low, medial because it's right in the middle, see greater activity in this region in older adults when there was high levels of retrieval demand, high memory load. It looks like this. And so we see more activity in the older group than in the younger group. When do we see it? Specifically on trials where we had to wait longer to make the choice. And only on that condition, not on the other ones. Ordinarily, we just call this attempted compensation. I might be using 2 hands, but am I actually doing the job better? Is it actually helping me? Or maybe it's interfering somehow. So if you just see overactivation or increased activation, that could still mean that it's not really helpful. It's just a difference in response. A difference in we have like a mismatch between supply and demand. What we need to determine whether this compensation is actually helping people is to map that activity onto something that indicates how high their performance was. So, do the best participants in the group have that activity or not? And they do. Successful compensation is what I care about. Did the activity help them do the task better? This is their reaction time. So with greater activity in the ventromedial prefrontal cortex, the faster they were, the shorter those response times were. So remember, I told you accuracy was similar across my younger and older adults, but the older adults were a little slower on average. The fastest ones, the ones that did it accurately and quickly, are the ones who had this higher level of ventromedial prefrontal cortex activity, which means it was helpful, which means it was successful in this compensatory process. On top of that, we can do things called connectivity analysis. We look at the brain region that seem to have this helpful activity and say, who's it talking to? And it's a pretty simple way to figure that out. We just say, which brain regions have activity levels that are related to this one? They go up when it goes up, they go down when it goes down. It's a simple correlation. That indicates that those regions are doing like the same thing. Maybe they are communicating with each other. Maybe their neurons are having a connection with each other. And we find that this dorsolateral prefrontal cortex area, right here on the side, on the outer edge, had corresponding activity. And guess what? This region right here, we know from a lot of data, it's one of the ones that aging hits the hardest. So it's not like using two hands to pick up the weight. It's like grabbing your friend from out of the river. I'm pulling along the region that's having the most trouble. That is what we think is going on there. How can we be more sure? Well, we can look at the activity, that connectivity between the two of them, how much they talk to each other, and see if it predicts anything important. It predicts external measures of decision competence, including people's comprehension of decision problems. The more connectivity, the better that people did that task. This is just my older adults, by the way. It also predicts cognitive reflection performance. These are these kinds of tasks where I ask you what seems like a simple math question, but the easy answer is the wrong one. And so they're very difficult. And people's performance on that task corresponded to the connectivity between these regions. So not only did we predict performance in our task that they did in the scanner, we predicted how well they're likely to make decisions in the real world that require things like inhibition, that require things like mental math and numerical comprehension. So this one we see is associated with inductive and arithmetical reasoning and abilities to engage in analytical thinking over intuitive thinking, not giving that knee-jerk reaction, but giving the more thoughtful one. So the evidence here on study number 3, optimally aging brains can compensate for declines in function. We see that the ventromedial prefrontal cortex is one of the regions that seems to be able to help out. It can help along regions that might be having more trouble, and it can help older adults to perform at equivalent levels to young if they are able to recruit it on board. So, some overarching lessons from my research. Healthy older adults seem to be able to exhibit adaptive neurofunctional responses to external pressures like stress. Again, stress might seem like a negative thing, but it actually is a helpful and functional response. So we see that in our healthy seniors. Some brain regions, not all, show little or no decline in functional abilities, even in folks who are on the average about 72 to 74 years old. And optimally aging brains also have this ability to compensate for their weaknesses. So this is what we hope for. We want to be able to leverage these findings It's not enough to just say, okay, this is how it reorganizes itself. But actually making some prescriptions about these are the kinds of tasks on which you'll do best. I'm going to tell you something that isn't in this data presentation. We asked our participants in the compensation study, what was your strategy? How did you remember the product that you saw several trials ago? And you know what they told me? The ones who did it the best, who activated that region the most, made little stories to themselves about the products. They attached this self-relevant information like, that was a little cat carrier, and I have a cat, and I've got a carrier just like that one. It was highly rated. It reminds me of the one that I have at home. And when they did these extra little associations with things that were relevant to them, they're the ones that had the highest levels of activity in those regions. Those are things that you can use as a strategy in your own life. Make these things self-relevant. Get the feedback right away. Demand applause the moment that you finish your talk. Well, now you're early, so we can't really study it. All right. So let's go back. Big picture. This is not healthy aging. And I want to tell you, just in case you think I'm super rude, the guy who picked this picture out, we had a whole discussion about it, okay? So I have his blessing to use this as an example because his conception of what cognitive aging is similar to a lot of people's. It's a normal kind of stereotype that we have, but it's not the reality. It's more like this. The aging brain is undergoing this constant adaptive process, and we have basically endless possibilities. So with that, I want to thank my mentors at USC, at Duke, collaborators on the projects that I've spoken with you about. Definitely want to thank the National Academy of Sciences for the opportunity to speak with you today and the selection committee for choosing me as your speaker. I want to thank the National Institute on Aging and all of your tax dollars because my work is not possible without it. Our participants, hundreds of younger and older adults who've done our studies, my own lab, the Adult Development Decision Lab at UCF in Orlando, and my family and friends for all the years of support. And I want to thank you for your attention.